Okay, we're picking up where we left off in Chapter 4, talking about oxidation-reduction reactions. In this video, we're going to talk about types of oxidation-reduction reactions. Okay, among the most common oxidation-reduction reactions are combination, decomposition, combustion, and displacement reactions. A more involved type is called disproportionation reactions, which will also be discussed in this section. Okay, so this chapter is about reactions in aqueous solution, with one of the main types of reactions that occur in aqueous solution being redox reactions. However, as we've seen, the textbook is sort of going over redox reactions in general here in this chapter. So in this section as well, we aren't just talking about redox reactions in aqueous solution, okay? So in general, in any environment, the most common types of redox reactions fall into one of 5 categories: combination, decomposition, combustion, displacement, and disproportionation. So a combination reaction is a reaction in which 2 or more substances combine to form a single product. So with a combination reaction, the general idea is you have multiple reactants combining to form a single product. So compounds have been combined. Okay, but now you can see here that neither of these reactions are in aqueous solution, right? To be dealing with a reaction in aqueous solution, the idea is at least one reactant or product needs to be aqueous. Okay, and now that we're comfortable with assigning oxidation numbers, we could go through each of these reactions, right, and assign all the oxidation states and analyze the redox properties easily. So on the reactant side, we've got all elemental forms, neutral elemental forms. So the oxidation number is going to be 0. Here we've got SO2. So there's nothing that's forcing us to go away from the oxygen cardinal rule of the oxidation number on oxygens being -2. So we put a -2 in the 2 oxygens. Then the sum rule dictates that the sulfur oxidation number must be +4. Here, aluminum is not a cardinal rule, but it's close to a cardinal rule. And aluminum will always have an oxidation number of +3 unless some other more stronger rule forces aluminum to have a different oxidation number, but bromine will not do that. So we put a +3 on the aluminum, and the sum rule dictates an oxidation number of -1 on the bromines. So, okay, we can see the oxygens here are reduced, the sulfurs are oxidized, or the oxygen acts as the oxidizing agent of oxidation for the sulfur, and the sulfur acts as the reducing agent for the oxygens. Here, bromines are reduced and the aluminums are oxidized. We can also look at the numbers of electrons transferred. You have 4 total electrons being skewed away from sulfur, 2 each being shifted towards an oxygen atom. Here you've got 6 total electrons being shifted away from 2 aluminum atoms, with 1 of those 6 electrons going towards a bromine atom. Okay, next we have decomposition reactions. Decomposition reactions are the opposite of combination reactions. Specifically, a decomposition reaction is the breakdown of a compound into 2 or more components. So with a decomposition reaction, you're starting with a single compound on the reactant side, and that compound is breaking up into 2 or more products on the product side. And like it said, this is the opposite of combination in that you're starting on the reactant side with a combination reaction with 2 or more compounds, and all of those compounds are combining into a single compound on the product side. Okay, and once again, none of these reactions are occurring in aqueous solution, just to point that out, but they could have been. You could have a combination or decomposition reaction take place in aqueous solution. So, for example, a combination reaction in aqueous solution would be something like the reaction of solid calcium oxide with liquid water to form an aqueous solution of calcium hydroxide. So there's a combination redox reaction that occurs in aqueous solution. Okay, decomposition reaction in aqueous solution would be something like the decomposition of carbonic acid in carbonated water into H2O and carbon dioxide gas. So H2CO3 aqueous decomposes into H2O liquid and CO2 gas. So there's a decomposition redox reaction in aqueous solution. Okay, a combustion reaction is a reaction in which a substance reacts with oxygen, usually with the release of heat and light, to produce a flame. Okay, but note that for a combustion reaction, we're most familiar with, you have a substance reacting with, like shown here, you have a substance reacting with oxygen to produce CO2 and H2O. That's what we're most familiar with when it comes to a combustion reaction. And we're most familiar with this because this is the combustion of hydrocarbons like gasoline, natural gas, diesel, wood, etc. But a combustion reaction is really more about a substance reacting with oxygen, usually producing heat in a flame. Okay, like it says, the reactions between magnesium and sulfur with oxygen described earlier are combustion reactions. So if we come back, this reaction here, solid sulfur combining with O2 gas to produce SO2, this is the combustion of sulfur. So you see there's no CO2 or H2O produced. All you get is just SO2 produced, and there's going to be heat released. Then also, if we come to this reaction from earlier, you have magnesium, solid magnesium reacting with oxygen to produce magnesium oxide and heat in the process. This is a combustion reaction. Once again, there's no CO2 or H2O. Okay, but again, what we're most familiar with is the combustion of hydrocarbons. So here, propane is a hydrocarbon. So you have carbon and hydrogen molecules combining with oxygen, and in general, you're going to produce CO2 and H2O in the process. Depending on the nature of the combustion, you could produce carbon monoxide, but in general, for an efficient, typical combustion process of a hydrocarbon, it's just the hydrocarbon plus oxygen results in CO2 plus H2O with heat released. Okay, but it says assigning an oxidation number to carbon atoms in organic compounds is more involved. So what do they mean by that? Well, okay, let's go ahead and assign oxidation numbers here. So, okay, we have the elemental form of oxygen. This is going to have oxidation number of 0 on each oxygen. Okay, now, if we come to the propane, yeah, this is a little bit tricky. So, how do we assign oxidation numbers here? We can do this, though. Yes, this is beyond the scope of what was taught in this textbook, but we went beyond what was taught in this textbook. And so we have the skills to assign the correct oxidation numbers here. So in this case, it's going to be useful to draw out the entire structure of the molecule. So we've got okay. So now first we can go ahead and analyze the hydrogens by comparing the electronegativities of hydrogen to carbon. These are all carbon-hydrogen bonds. So looking at the electronegativity chart, carbon is more electronegative than hydrogen. So we're going to put a +1 on each of the hydrogens. Okay, now we could go straight to the sum rule to determine the oxidation numbers on the 3 carbons. In that case, if we assume the oxidation numbers on the 3 carbons are all the same, equal to x, then we would get 3x is equal to -8, so x is equal to -8/3. And if this molecule was fully symmetrical with respect to the hydrogen bonds on all of the carbons, then we would say that the oxidation number on each carbon is -8/3. But we can analyze this further. Because remember another rule that was mentioned, another cardinal rule that was mentioned, is that for a bond between the same element, if you have any bond in a molecule that's between the same element, like here a carbon-carbon bond and here a carbon-carbon bond, then we assume that within that bond there's no skew of electrons in either direction along that bond. Okay, and so with that then, well, okay, we have these cardinal rules for hydrogens established, the hydrogens. So like for this carbon, you're going to have a skew of 1 electron each coming from each hydrogen, right? But then there's going to be no skew here. So the oxidation number on this carbon has to be -3, and on this carbon also has to be -3. Now here we've got no skew here, a skew of 1 electron from each hydrogen here. So this has to be -2 on this carbon. But I mean, even the sum rule, like if we stopped here with the -3s and did the sum rule would say this is -2 anyway. So it works out perfectly. And so there's the oxidation numbers. Okay, now on CO2 and H2O, we would have a -2 on the oxygens, resulting in a +4 on the carbon. Here on the H2O, we would have a +1 on the 2 hydrogens and a -2 on the oxygen. And so we could see we've got carbons being oxidized and oxygens being reduced. Okay, now a displacement reaction. In a displacement reaction, an ion or atom in a compound is replaced by an ion or atom of another element. Okay, so it's saying an ion or an atom because the displacement can occur in regards to like ionic compounds, but also molecular compounds. Okay, but this term displacement reaction might sound familiar. If we come back to the section 4.2, the start of section 4.2 on precipitation reactions, we see that. So here was a typical precipitation reaction in aqueous solution that we looked at, the type of problems that we worked. And so this type of reaction is what's called a metathesis reaction, also known as a double displacement reaction, a reaction that involves the exchange of parts between the two compounds. So here, this is a displacement reaction, specifically a double displacement reaction. Okay, and so note that in general, double displacement reactions are not going to be redox reactions, right? The precipitation reactions here are not redox reactions. In a double displacement reaction, you're just going to have an exchange of positive and negative ions or atoms in positive or negative oxidation states to form new compounds. Same idea with the acid-base neutralization reactions we studied. These were all double displacement reactions, right? If we look here, you've got hydrogens, atoms, not ions, atoms, because you don't have an ion here on HCN. It's a hydrogen in a positive oxidation state just moving to being bonded with oxygens as a hydrogen in a positive oxidation state, right? You're just swapping out atoms here between these two compounds. So this is a double displacement reaction, but it's not a redox reaction. Okay, but the displacement reactions that they're talking about here, so displacement reactions that are redox reactions, here they're specifically referring to single displacement reactions. In general, if you have a single displacement reaction, then it's going to be a redox reaction. And it's going to involve an elemental form of a substance as one of the reactants. Another reactant is going to be a compound with more than one element. Then you're also going to have a reactant that's an elemental form. And after the chemical reaction takes place, atoms in the elemental form swap places with one of the atoms of an element in the compound form. Okay, so it says most displacement reactions fit into one of three subcategories: hydrogen displacement, metal displacement, or halogen displacement. Okay, so let's make sure to get the terminology clear here, because the terminology can be confusing with displacement reactions. Okay, if an element is said to be displacing another element, then the element in the elemental form is displacing the element in the compound form. I always had a natural tendency to think about it the other way around, because you would think a stable element like gold would be the strongest at displacing other elements, right? But according to this terminology, it's the other way around. Gold is an element that's most easily displaced by other elements. Gold can easily be taken out of a solution, taken out of a compound, and displaced by another element. Okay, so first they talk about hydrogen displacement reactions. But we can really think about hydrogen displacement and metal displacement reactions at the same time. So if we come here to what's called the activity series for metals, so you have an activity series for metals and also an activity series for nonmetals, or specifically the activity series for halogens, which we'll discuss next. These aren't the only two activity series, but these are two of the most common ones. But the activity series for metals organizes metals relative to one another based on their reactivity from most reactive to least reactive. It's used to summarize information about the reactions of metals with acids and water and with other metallic compounds, like the extraction of metals from their ores, for example. Specifically, the activity series for metals is summarizing how metals behave with respect to single displacement reactions. Okay, and so with the inclusion of information about how metals react with acids and water, hydrogen then is also included in the activity series. So in the metal activity series, hydrogen serves sort of like a chemical reference point to determine a metal's reactivity with water and acids, and also as a reference point for separating more reactive metals from less reactive metals. Right, so you can see how the hydrogen is used as a general reference point for how reactive other metals are with respect to what they talk about here with respect to hydrogen, and then as well as with respect to other metals on the chart. Okay, and so the idea is the higher a metal is in the activity series, the higher up on the activity series, then the stronger is its ability to displace other metals or hydrogen in a single displacement reaction. Technically, if a metal is just above another metal, just one slot above another metal or hydrogen in the series, then the metal can displace that metal or hydrogen in a single displacement reaction. But also just note how hydrogen is above some other metals in the series. So in some cases, you could have hydrogen with the ability to displace these metals in a single displacement reaction. Okay, now also the distance in which two metals are apart from one another matters. So if you had elemental potassium, for example, just an elemental form of solid potassium in a solution with a dissolved mercury compound, so you had mercury in dissolved and there were mercury Hg2 plus ions floating around. Well, because those two metals are far apart from each other on the activity series, then what's going to happen is you're going to get a relatively strong, favorable, intense reaction, as opposed to if you had an elemental potassium immersed in an aqueous solution with a dissolved barium compound. So elemental potassium with Ba2 plus ions. Yes, the potassium is able to displace the barium. Potassium is above barium in the activity series, but in general, the reaction is going to be slower and less intense. Okay, and so if we come back to part one, hydrogen displacement, single displacement reactions. So part one and part two of this section on single displacement redox reactions, part one and part two talk about hydrogen displacement and metal displacement reactions, which both of these types of reactions are based on the metal activity series. And hydrogen displacement are just single displacement reactions in which a metal is displacing hydrogen from a compound or vice versa. Whereas metal displacement is just when a metal is displacing a metal from a compound. But again, it's all based on the hydrogen displacement and metal displacement reactions we're talking about here are all based on this same activity series, the metal activity series. Okay, and remember, again, with a single displacement reaction, what's happening is you have atoms in an elemental form of a substance replacing atoms of an element in a compound form. Okay, but now you might ask, can these single displacement reactions only occur in aqueous solution? Well, no, they can occur in any scenario, in any environment. Yes, an aqueous environment would be an ideal environment for facilitating a single displacement reaction to occur because of the mobility of dissolved ions. But any scenario where species can interact in a way that will allow a reaction to occur, if that reaction is energetically favorable, so favorable in this sense of in terms of location of the species on the activity series, then that's a scenario or an environment where a single displacement reaction can occur. Okay, so hydrogen displacement reactions. So we're thinking about single displacement reactions on the metal activity series that involve hydrogen. Most of the time it's going to be hydrogen being displaced by a metal, but it could also involve hydrogen displacing a metal as well. So it says all alkali metals and some alkaline earth metals like calcium, strontium, and barium, which are the most reactive of the metallic elements, will displace hydrogen from cold water. Okay, so yes, if we come back to the activity series, you've got many metals above hydrogen, right? But some are farther above hydrogen than others. And remember, distance from another element on the activity series matters in terms of the strength of the energetic favorability of that reaction. So what they're saying is, at the top here, you've got the most reactive metals. So that would be alkali metals and some of the alkaline earth metals. These will displace hydrogen from cold water, react with cold water to produce H2. Okay, so as this shows, these chemical equations show, if you add elemental sodium or elemental calcium to water, and in this case we can think about the water being cold, which what they're implying is that this isn't as favorable of an environment for allowing chemical reactions to occur if the water's cold. Okay, but with elemental sodium or calcium added to cold water, chemical reactions take place in which you have sodium and calcium atoms pushing hydrogen atoms out of water molecules, displacing hydrogen atoms, with the sodium and the calcium then forming compounds, so sodium hydroxide and calcium hydroxide, and then the pushed out hydrogen is forced into its elemental form, H2 gas. Okay, but now if we come back to the activity series, metals that aren't quite as reactive as metals that can displace hydrogen from cold water are able to displace hydrogen from a hot water environment, like steam, right? High temperature H2O. Or if you've got some metals that aren't reactive enough to even displace hydrogen from hot water, some metals are still reactive enough to displace hydrogen from an acidic solution, which this would be even more favorable for displacing hydrogen because you've got excess H plus ions everywhere, as opposed to with just pure water, it's a neutral environment with respect to H plus. Okay, and so it shows here how you've got solid zinc and magnesium in a hydrochloric acid aqueous solution, and the result is the zinc and magnesium atoms displace the hydrogen atoms from the compound, and they enter the solution to form zinc and magnesium chloride, and the hydrogen atoms are pushed out into their elemental forms, H2 gas. Okay, but again, if we come back to the table, zinc and magnesium are able to displace hydrogen from steam, just a neutral water, hot water environment, but in a cold water environment, no reaction is going to happen, right? But if you've got a metal that can displace hydrogen from cold water or steam, then that metal can also displace a hydrogen from an acid, right? Alkali metals can absolutely displace hydrogen from acids. It's actually going to be a relatively more intense reaction, okay? So it says figure 4.15 shows the reactions between hydrochloric acid and iron, zinc, and magnesium. These reactions are used to prepare hydrogen gas in the laboratory. Okay, so in the activity series here, we've got, they're referring to iron, zinc, and magnesium. So you can see that magnesium is more reactive than zinc, which is more reactive than iron. Now, if we come here, they've put elemental iron and zinc and magnesium into hydrochloric acid solutions, and you can see the result. You've got H2 gas bubbling out in all cases, but it's more intense here. It's more intense reaction of the gas coming out in magnesium versus zinc versus iron. Okay, now metal displacement reactions. Again, this category is referring to the exact same metal activity series, but now it's just that hydrogen is not involved in the reaction, in the displacement. You have metals displacing other metals. Okay, so a metal in a compound can be displaced by another metal in the elemental state. We have already seen examples of zinc replacing copper ions and copper replacing silver ions. Okay, so those reactions they're talking about are shown here. We looked at these earlier. So you've got zinc, solid zinc in a copper 2 sulfate solution, and because zinc is above copper in the activity series, zinc displaces copper out of the solution. Okay, and then same with, you've got solid copper in a silver nitrate solution. Because copper is above silver in the activity series, the metal activity series, the copper displaces the silver out of the solution. Okay, but now it says reversing the roles of the metals would result in no reaction. Thus, copper metal will not displace zinc ions from zinc sulfate, and silver metal will not displace copper ions from copper nitrate. Yeah, so this is not a reversible reaction. If you started off with solid copper in a zinc sulfate solution, nothing's going to happen because copper is below zinc in the activity series. It can't displace zinc. Okay, an easy way to predict whether a metal or hydrogen displacement reaction will actually occur is to refer to an activity series. So here they introduced the activity series. Again, it's an activity series, just a convenient summary of the results of many possible displacement reactions. Right? What can and will displace what in a displacement reaction? Okay. So now it says, metal displacement reactions find many applications in metallurgical processes, the goal of which is to separate pure metals from their ores. For example, vanadium is obtained by treating vanadium 5 oxide with metallic calcium. So you've got vanadium oxide, solid vanadium oxide, combined with elemental calcium, and the calcium displaces the vanadium. Okay, but for example, here's a displacement reaction that's not taking place in aqueous solution, right? It's a good example, right? It's not about aqueous solution, just solutions lend themselves to these types of reactions taking place because you've got the mobilized species, but you can have any kind of displacement reaction take place if it's energetically favorable, according to the corresponding activity series, as long as the components can interact well enough and run into each other so that the reaction can take place. So you've got like a liquid calcium with solid vanadium oxide mixed in, right? So everything can intersperse and intermingle. Similarly, titanium is obtained from titanium 4 chloride according to the reaction. So you've got liquid magnesium and titanium chloride gas dissolved, right? That's a good enough environment to, if it is energetically favorable, so magnesium is above titanium in the activity series, so the magnesium displaces the titanium. Okay, and so it says, in each case, the metal that acts as the reducing agent lies above the metal that is reduced in the activity series. And so this is another important perspective to view these single displacement redox reactions, or to view the metal activity series, and as we'll see in a second, to view the non-metal halogen activity series. Okay, because it says here, as you go up the table, as you go up to more reactive metals, the reducing strength increases. Okay, another way to state that the reducing strength is increasing is that as you go up the table, you have stronger reducing agents, right? Because as you go up the table, you have more and more reactive metals. At the top, the alkali metals which are the most reactive metals. Okay, well, why are alkali metals so reactive? Well, because they readily will give up that outer valence electron, right? They have a strong tendency to therefore be oxidized in a chemical reaction. Well, if they're oxidized, then that means they're at the same time reducing some other element, right? So you also state that alkali metals have a strong tendency to reduce other elements or to act as reducing agents. Okay, this categorization is really clear from the perspective of extracting metals from their ores, right? Because what you need to do in these cases, you're needing to reduce vanadium and reduce titanium, or reduce gold, or reduce silver. So what you need is, to make this happen, you need a reducing agent that will reduce these elements for you. And that's exactly what calcium and magnesium are doing in these cases. Okay, now the third category of single displacement reactions is halogen displacement reactions. Again, two of the most common activity series are the metal activity series and the non-metal halogen activity series. Okay, now as an activity series, the quote-unquote table for halogens is just the halogen column in the periodic table. So if a halogen is above another halogen in the halogen column, then that halogen is considered more reactive and will therefore displace a halogen below it from its compound if the conditions allow for enough interaction between the species. Okay, but now this is a little bit different from the metal displacement reactions and the metal activity series, in that in this case a more reactive halogen is a strong oxidizing agent, not a strong reducing agent. Okay, so when a halogen displaces another halogen from a compound, it does so by oxidizing that other halogen into its elemental form, not reducing it like we saw with metals. So like, for example, here we've got chlorine gas dissolved in you have an aqueous solution, aqueous potassium bromide solution, and an aqueous sodium iodide solution. So here we've got dissolved halides, right? Bromide, iodide, those are halogens, but in the negative oxidation state, so halides. Okay, then you also have Cl2 gas pumped into, mixed into the solution. Okay, but then because chlorine is above bromine and iodine on the halogen activity series, chlorine will push the bromide and the iodide out of their compounds, out of the solution, into their elemental forms, and then enter the solution or enter into the compound. Okay, but you can see how this is different from the metal displacement reactions, because the metals were displacing the cation, or the positive oxidation state component of the compound, right? But in this case, the halogen is displacing the anion, or the negative oxidation state component. And therefore, to push that negative species out, it has to oxidize it. So the bromide and the iodide got oxidized in order to be pushed into their elemental forms. And then the chlorine at the same time gets reduced. It becomes a chloride. Okay, but now note how it says molecular fluorine is so reactive that it also attacks water. Thus, these reactions cannot be carried out in aqueous solutions. So you couldn't carry out a reaction like shown here in aqueous solution with chlorine using fluorine, because fluorine is so reactive, it's such a strong oxidizing agent, it will actually attack the water molecules themselves as well. So when it says fluorine attacks water, what do you think that means? Well, fluorine being so reactive, we know means that it's a very strong oxidizing agent. So what part of water can be oxidized? Well, it has to be the oxygens, right? You can't oxidize hydrogens in water any more than they're already oxidized. And so just to show you, the reaction of dissolved fluorine gas in pure water is given by, so you've got the fluorine gas and water gives And we put a 2 here. Okay, so when elemental fluorine interacts with water, this is what happens. That's what they're talking about, how fluorine will attack water. And actually, interestingly, with excess fluorine gas dissolved in water, you have a reaction given by so fluorine attacks the water to produce, once again, hydrofluoric acid, but not O2, in this case, O3, ozone, which we know is an allotrope of oxygen. Okay, and so this is, when there's excess fluorine, then you can think about this reaction is also taking place. If there's an excess amount of elemental fluorine gas mixed in with just water. Okay, and so now next, what they do is they just present the net ionic equations for these two reactions here. So there's the net ionic equations, which, as we know, this just gives us a clear picture of the overall chemical reaction that takes place in the solution. Okay, now next it talks about how, so since bromine is above iodine in the halogen column, that means that molecular bromine can displace iodine if the conditions facilitate the interaction of the species to allow the chemical reaction to take place. And here they give the corresponding net ionic equation for the displacement of iodine or iodide, iodine as a halide, by elemental bromine. Okay, now reversing the roles of the halogens produces no reaction. Thus, bromine cannot displace chloride ions, and iodide cannot displace bromide and chloride ions. Right, just like with the metal activity series, you aren't going to have a single displacement reaction take place where an element below an element in the activity series displaces an element above it. In such an environment, a reaction just won't take place. Nothing will happen. Okay, the halogen displacement reactions have a direct industrial application. The halogens as a group are the most reactive of the nonmetallic elements. They are all strong oxidizing agents. As a result, they are found in nature in the combined state with metals as halides and never as free elements. Yeah, so halogens are used in society for different applications. And they're strong oxidizing agents because they're one electron away from a noble gas configuration, similar to how alkali metals are strong reducing agents since they're also one electron from a noble gas configuration. Okay, now because halogens are such strong oxidizing agents, in nature you find them in compounds combined with other elements that they've oxidized. And therefore, by oxidizing these other elements, the halogens are themselves reduced and exist as halides, or in negative oxidation states in nature. Okay, of these four main halogens, the fluorine, chlorine, bromine, and iodine, chlorine is by far the most important industrial chemical. In 2010, the amount of chlorine produced in the United States was about 25 billion pounds, making chlorine the 10th ranking industrial chemical. The annual production of bromine is only 1/100th that of chlorine, while the amounts of fluorine and iodine produced are even less. Okay, but so in nature, you've got halogens in the halide form. And so recovering the halogens from their halides requires an oxidation process, which is represented by this. This is the corresponding oxidation half reaction for when a halide is converted to its just normal halogen form. It's taken out of a compound in nature. Okay, now just a quick reminder, it's not like half reactions have to involve ionic compounds and ions. You can construct half reactions for any redox reaction, even if no compound or actual ions are involved. Okay, however, in nature, halogens are typically going to be found as salts, which as we know are ionic compounds. And so the oxidation half reaction for extracting a halogen from a salt would be you've got two halide ions. So X is any halogen or halide. Those two halide ions each give up a single electron. So you have two electrons, and then the neutral halogen atoms bond together to form X2. So like F2, Cl2, Br2, I2, which is what you're wanting to get, right? You're trying to recover pure halogen in its elemental form, right? And so like the elemental form of a halogen is the majority of the time going to be a diatomic molecule, where you have a single electron is shared between the atoms, so that both have a noble gas configuration. Okay, seawater and natural brine, for example, underground water in contact with salt deposits, are rich sources of chloride, bromide, and iodide ions. Minerals such as fluorite and cryolite are used to prepare fluorine. Because fluorine is the strongest oxidizing agent known, there is no way to convert fluoride ions to F2 by chemical means. The only way to carry out the oxidation is by electrolytic means, the details of which will be discussed in Chapter 18. Industrially, chlorine, like fluorine, is produced electrolytically. So yeah, recovering the elemental form of chloride, bromide, iodine from their compounds, you can't do this chemically. You can't convert fluoride to F2 chemically because there's no stronger oxidizing agent available. So this is done, like it says, electrolytically, which we'll learn about in Chapter 18. But it's also economical at the same time to oxidize chloride electrolytically as well. Okay, so bromine is prepared industrially by oxidizing bromide ions with chlorine. So this is done chemically, which is a strong enough oxidizing agent to oxidize bromide ions, but not water. Yeah, so that's true. It's not that chlorine, it's more economical to use electrolytic means to oxidize chlorine, but it was that fluorine attacks water. You can't use fluorine as an oxidizing agent. So fluorine doesn't have a stronger oxidizing agent to oxidize it. And then chlorine, there is a stronger oxidizing agent, fluorine, but fluorine attacks water. So it makes it difficult. So both are extracted electrolytically. Okay, but bromine is prepared industrially by oxidizing bromide ions with chlorine, which is a strong enough oxidizing agent. Yeah, so and it doesn't attack water. So here's the oxidation half reaction. You've got two bromide ions, each give up an electron. So you have two electrons given up, and the resulting bromine atoms bond together to form liquid Br2 liquid bromine. Okay, one of the richest sources of bromide ions is the Dead Sea. About 400 parts per million by mass of all dissolved substances in the Dead Sea is bromine. Following the oxidation of bromide ions, bromine is removed from the solution by blowing air over the solution. And the air-bromine mixture is then cooled to condense the bromine. Interesting. Iodine is also prepared from seawater and natural brine by the oxidation of iodide ions with chlorine. Because bromide and iodide ions are invariably present in the same source, they are both oxidized by chlorine. However, it is relatively easy to separate Br2 from I2 because iodine is a solid that is sparingly soluble in water. The air blowing process will remove most of the bromine formed but will not affect the iodine present. Interesting. Okay, now the last type of oxidation-reduction reaction, we had combination, decomposition, single displacement. We just finished with single displacement. Now we want to look at disproportionation reactions. A special type of redox reaction is the disproportionation reaction. In a disproportionation reaction, an element in one oxidation state is simultaneously oxidized and reduced. One reactant in a disproportionation reaction always contains an element that can have at least 3 oxidation states. The element itself is in an intermediate oxidation state on the reactant side. That is, both higher and lower oxidation states exist for that element in the products, right? Because it's going to be in you're going to have an element either in an elemental form or contained within a compound. And on the reactant side, it's going to be in an intermediate oxidation state, but then because it's a disproportionation reaction, that element is going to be simultaneously both oxidized and reduced. So on the product side, you're going to find that element in a higher and lower oxidation state. The decomposition of hydrogen peroxide is an example of a disproportionation reaction. So you've got so what they're saying is that you can't have, since we've got the oxygen is going to be the element involved in the process of being both oxidized and reduced. And so if you think about the potential oxidation state chart, what they're saying is that it's necessary to have the element that's going to be both oxidized and reduced have at least 3 possible oxidation states, like oxygen does, or any of these elements with more than 2 oxidation states. Because otherwise it's not going to work, right? You have to start with 1 oxidation state on the reactant side and then go to 2 different oxidation states on the product side. And that's what happens here. You're starting with oxygen in a -1 oxidation state, because here with H2O2, the hydrogens are going to, their cardinal rule is going to be obeyed first. They're bonded to oxygen, which oxygen has a higher electronegativity. So these take on an oxidation state, hydrogens take on an oxidation state of +1. The sum rule then dictates that the oxygens have an oxidation state of -1. But then when the reaction takes place, if you go assign the oxidation numbers, here H2O, oxygen has oxidation number -2. Here O2, it has oxidation number 0. So there you go. Oxygen is both oxidized and reduced in this reaction. Okay, another example is the reaction between molecular chlorine and sodium hydroxide. Here, if you go through and assign all of the oxidation numbers, chlorine is both oxidized and reduced. This reaction describes the formation of household bleaching agents, for it is the hypochlorite ion that oxidizes the color-bearing substances in stains, converting them to colorless compounds. Interesting. Okay. Finally, it is interesting to compare redox reactions and acid-base reactions. They are analogous in that acid-base reactions involve the transfer of protons, while redox reactions involve the transfer of electrons. However, while acid-base reactions are quite easy to recognize because they always involve an acid and a base, there is no simple procedure for identifying a redox process. The only sure way is to compare the oxidation numbers of all the elements in the reactants and products. Any change in oxidation number guarantees that the reaction is redox in nature. Yeah, so an acid-base neutralization reaction, you just need to, it's going to involve an acid and a base coming together and reacting. Well, just looking at face value of a general chemical reaction with nothing else, just a balanced chemical reaction, you can't just automatically look at the compounds and state this if this is a redox reaction or not. However, with oxidation numbers, if you go through and quickly assign the oxidation numbers to all of the atoms in every compound of the reactants and products, well, then it's easy. Because as we've talked about, if there's any change in oxidation number whatsoever, if you're tracking the same element in with respect to reactants and products, if there's any change in oxidation number, no matter how much the change is, it's a redox reaction. If there's no change, then it's not a redox reaction. And that's what we saw with the precipitation reactions that we studied and the acid-base neutralization reactions we studied. There is no change in oxidation number. So those weren't redox reactions.